Today we're going to start our unit on quantum physics. Quantum physics, you're going to find a lot of things that are really interesting. We're going to need to lay the groundwork first, so we're not going to start quantum today. I just want you to know in quantum physics we're talking about focusing on the electrons. So we've already focused on the nucleus inside an atom. With quantum physics we are going to be looking at how the electrons behave both inside and outside of the atom. Before we can do that, you need to be really fluent with some wave ideas, so I'd like to review some of the really basic stuff we learned last year, starting with what is a wave. A wave is a disturbance that propagates through space and time. So in one dimension, we're going to have a wave traveling through a slinky. In two dimensions, we're going to have the wave traveling along the surface of a pond. So if you watch Mr. Manton, he sends a disturbance through the slinky. The disturbance doesn't stay localized, but propagates along the slinky. We're going to throw a rock into the pond. The disturbance that happened right here travels through space and time. Realize it is a transfer of energy, not a transfer of matter. No matter actually traveled from Mr. Manton's hand to the other end of the slinky. It was only energy that traveled from place to place. Because it is only energy, waves have the unique ability to occupy the same place at the same time. So as we watch these waves come in and bounce off of the barrier, you can see that they go right through each other. Two waves can occupy the same place at the same time. Four things you need to be able to remember and use when we're talking about waves. They are the amplitude of the wave, the wavelength of the wave, the period, and the frequency. Reminder, amplitude tells you the height, the wavelength tells you the distance from one wave to the next successive wave, period tells you how much time there is in between waves, and frequency tells you the number of waves that occur per second. Remember that these two are linked together because they are reciprocals of each other. If you know the frequency, you invert it and you get the period. So if you had 5 waves per second, the period would be 0.2, 1/5. Okay, so as you watch these waves go, again, amplitude is how high they are, wavelength is the distance in between, period is how many occur, period is the time it takes for one wave, and the frequency is the number of waves per second. Remember what some of these things tell you. Amplitude tells you how loud a sound is or how bright a light is. A larger amplitude is louder, a larger amplitude is brighter. Frequency. For sound, frequency tells you the pitch, and for light, frequency tells you the type or the color of the light. Remember that you cannot see all frequencies, so there's only a narrow band of frequencies that are visible to our retinas. The others are things like radio waves, microwaves, infrared. The visible, again, very narrow range from about 4.3 to 7.5 e to the 14th, 100 trillion, so about 430 trillion to about 750 trillion hertz cycles per second. I broke out the different colors of the visible spectrum, and then we get the ultraviolet, X-ray, and gamma ray, things we cannot see. Same thing with sound. There is a narrow range of sound frequencies that we can hear. They run from about 20 hertz to 20,000 hertz, and they are acoustic sounds. Infrasound is if you're below 20. Ultrasound is if you're above 20,000. Okay, ultrasonic means your frequencies are higher than 20,000. Don't forget, the speed of the wave depends upon what the wave is traveling through. So with sound waves, they have the highest speed when the material is solid, generally speaking. The particles are close together, and the energy can transfer very efficiently from atom to atom to atom. Sound generally travels slow in gases. When the gases are very light, the sound can travel much faster. When the gases are heavy, the sound travels much slower. With light, it's a little trickier. You figure out the speed of light with a thing called your index of refraction. You take the speed of light and you divide by the index. So for diamond, we would divide by 2.42, and that would tell us how fast the light travels through diamond. Okay, as a final thing to remember, the connection between velocity, frequency, and wavelength. Frequency is determined by the source. So each tuning fork might have a different frequency. Your guitar strings might have different frequencies. A light might have a certain frequency. Okay, so the frequency is determined by the source. The speed is determined by the material that the wave is traveling through. The fancy name for that, it's called the medium. It's the material that the light or sound or wave is traveling through. The medium determines the speed. The wavelength is the dependent variable. It depends on the speed, which depends on material, and the frequency, which was determined by our source. Okay? So that is the connection between velocity, wavelength, and frequency. Again, all these terms and ideas we covered last year, I want to freshen your head before we got any deeper into our study of waves. And again, our study of waves is a prelude to what we're going to be doing with quantum physics. We cannot understand quantum physics unless we understand these wave properties.